So here we are at the third of the lecture series, small angle scattering as a nanostructural tool. The third of these lectures is about theory. We'll try to keep it light, not so much mathematics. The mathematics that we have is rather important, and I'll try to keep the emphasis on pictures. So again, we go to the generic scattering experiment, and really what this lecture is going to be about is just understanding some properties of the transformation which leads from the sample structural properties to the scattering curve. And we'll draw out some simple rules about understanding the scattering curves. So if we consider the generic scattering experiment with a beam incident on the sample, which has some structure, and the beam is scattered and some pattern is collected on a 2D detector. The transformation, the big black box between the sample structure and the scattering curve, or the scattering cross-section that we measure. So we hope, by understanding the forward transformation from structure to scattering curve, we can apply a reverse transformation to get structure from the scattering curve. So in the first case, let's consider the interaction of two particles. And of course, objects are made up of many particles characterized by a spatial distribution or a spatial variation in density, rho of r. But let's consider these two waves and two particles. As a result of the interaction and the spatial distribution of these two particles, there's first of all a phase shift between the waves that have interacted elastically with the two particles. So the diagram there just shows simple geometry around that, the nature of that phase shift. And of course, one can quantify this with the momentum transfer vector. As the waves travel towards the detector, and as they reach the detector, there is this slight phase shift causes the waves either to constructively or destructively interfere with each other, causing a change in the intensity. This slide describes the relationship between what is the real space structure, or the spatial variation and scattering length density, characteristic of a sample volume, i.e. the shape and the contrast of the sample heterogeneities, that's what we want, and what we measure, which is intensity versus Q, or the scattering cross-section, which is the square of the amplitude, and the amplitude is the Fourier transform of the variation in scattering length density. Pictorially, one might think of it like this. So on the left-hand side, we have relatively dilute particles. They're a long way from each other. And if we do a Fourier transform of that, and indeed you can do that with the tools that I've shown you, the density fluctuations within the particle are important, i.e. the shape. The particles are not so close together that the density fluctuations between the particles become important. So that's the dilute limit, where the scattering is dominated by the form factor or the shape of the particles. Now, we haven't considered it in this case, but there can also be some internal variation in density of the particles, and you might like to play around with that. In the other case, where one simply adds more particles per unit volume, then the scattering becomes a product of the density fluctuations of the single particles themselves, and indeed the fluctuations within the particle, although that's not drawn here, and the density fluctuations between the particles. So formally, the density fluctuations within the particle are called the form factor, or P of Q, and the density fluctuations between the particles are called the structure factor. So thinking about that previous slide, you might like to think about how that would be done experimentally, how experimentally you'd be able to differentiate between scattering, which was due to the form factor, or just the internal structure of the particles, and scattering, which is due to the form factor multiplied by the structure factor, which is scattering due to density fluctuations within the particle and between the particle. It's a nice little experimental exercise. Mathematically, the intensity that we measure as a function of Q is just a very simple product of the number of particles in the sample multiplied by the volume of the particles squared. The next factor is the contrast, which measures the strength of the interaction, and we'll talk a little bit more about that in some detail later. The form factor, which is just the shape of the particles as we described before, and the structure factor. So in the dilute limit, the structure factor just equals 1. In more concentrated solutions, one has different kinds of expressions you can use for the structure factor. And that scattering is superimposed above an experimental background, which we shall talk about later. So in the next few slides, I'm going to give you a few useful relationships which describe the low Q regime of scattering, how big things are, and the high Q, which describes how much interface there is in a two-phase system. So the simplest of scattering laws is at low Q is the Guinier law, and that just describes a limiting law which relates the decay of the intensity close to Q equals 0 to the size of the object. And typically in the Guinier regime, as you see in the figure at the bottom, that the scattering curve begins to turn over towards some limit at I0. If the scattering vector is much too large for the Guinier approximation to be applicable, you don't see this turnover in intensity. And it's usually a very good indicator of whether you have some aggregation or polydispersity of size of the objects. So that turnover is a measure of the average size of the object. So the scattering curve of a particle of a particular size can be approximated by a Gaussian curve in the limit of Q approaching 0. Or to put it another way, if you plot ln Q intensity versus Q squared, the intercept can yield information about the radius gyration and the volume of scattering particles from a linear regression. The other limiting scattering law is at high Q. And what that says, as Q approaches infinity, that there's some limiting behavior which is related to the amount of surface area between the two phases. And taking the Gounier law as a cue, you might think about what the kind of plot that you would make to see what the limiting value is and what the surface area between the two phases is. And I've given you a reference there where this kind of approach has been used to determine the amount of surface area in a material. So here's the answer to my question. So of course you plot q to the power 4 multiplied by I against q. The low q regime in this plot is related to the Gounier radius, but as you go out to higher q, the line becomes parallel to the x-axis, and you could extrapolate that to get an idea of the surface area. That is, if you know the volume fraction of the two phases and the contrast between them. So in this slide, we'll consider the form factor of a sphere, and I've given an expression for that, and you could even look that up if you like. But what I'd really like to concentrate on is the scattering curve that's shown in the bottom figure. So you can see at low Q, the scattering turns over, and in fact at Q equals 0, that you might think is related to the transmission of the sample. And as it turns over, that's related to the radius of gyration of the sphere. Because these are monodispersed spheres, and I'll come back to the issue of polydispersity and what the effect of that on the scattering pattern is later, you see these oscillations, and the period of those oscillations is also related to the radius of the sphere. If you were to do a Fourier transform, and indeed you can do this with image J of different kind of spheres, you might like to look at what that radius has effect on the period of the oscillations. But the dotted line there, which has a slope of minus 4 on the log intensity log Q scale, is related to the surface area, the amount of interface between the sphere and the surrounding bulk, or the solution, if it's a solution of spheres. So let's consider the effects of polydispersity on the scattering solution. Actually, IUPAC now call it dispersity. We've lost the polydispersity, but because it's a familiar term, I'll use that anyway. Now, in your samples, polydispersity might be that you've made vesicles which are all not the same size, or if you have proteins, they may aggregate, or if you've made particles by some chemical process, you may see a distribution of sizes. That's what I mean by dispersity / polydispersity. So let's look at the effect of that on the scattering curve, how distribution affects those oscillations. So in the first case, let's think about a narrow size distribution of spheres. I've got two spheres there, and our solution might be a lot of those, and there's not much difference between the size of them. The first thing you'll notice is, compared to the form factor of a monodispersed sphere, is that fringe, those oscillations in the q to the minus 4 dependence have been smoothed out. And what you can think of is that the scattering pattern is actually a superposition of the two curves for each size class in that case, weighted by the volume fraction of each. So, of course, if we have a wide size distribution of spheres, and in this case we've got 4, naturally enough that oscillation is smeared out, and you just see the q to the minus 4 dependence. What this means in terms of scattering is that if you have a superposition of many form factors, it's very difficult to get the form factor out of a particular particle, which is to say you cannot determine polydispersity and the shape of particles from modelling the scattering curve. So if we put all this together, and what I've generated here is the scattering from a unilamellar vesicle, some abstraction which is quite monodispersed. There's no size distribution in these vesicles. They're spherical, and there's a thin layer between the inside and outside solution. So in the first case, at low Q, we see the radius of gyration of these vesicles. And because they're quite monodispersed, there'll be some oscillations. As we go to medium Q, we start to see a thin, flat layer. And as we go to lower Q still, we start to see scattering due to the thickness of the layer. And again, this is monodispersed and has some characteristic oscillations associated with the thickness. And superimposed on that, that's the dotted line, is that Q to 4 minus dependence, which reflects the amount of interfacial area between the vesicle and the solution. So we come back to my familiar analogy of blind men gathering local information. And in the case of the vesicle, the local information was the overall radius, and so that was at very low Q, large length scales. So the overall shape of the object could be seen, the radius of gyration in low Q. As the information becomes much more local, one starts to see the flat surface of the vesicle, and at more local information or at higher Q values, then one starts to see the structure associated with the thickness of the bilayer in the vesicle. So the information is Q dependent. At low Q, you see the overall shape of the object. At medium Q, the surface flatness, and at the highest Q, the thickness of the bilayer. That's in decreasing length scale. And indeed, over an extended Q range, the log-log plot and its slope can describe many characteristic dimensions. So a slope of 1 is characteristic of a rigid rod. A Gaussian chain or a normal polymer chain has a slope of 2, and so on. So this log-log description can be quite useful in understanding the shape of the object at that particular, or the fractal dimension of the object at that particular length scale. So in summary, from this simple and I guess a little bit superficial survey of the theory, the scattering curve is a Fourier transform of the real space density distribution function. For dilute particles, that's particles that are a long way away from each other, and there's no density fluctuations which are due to intercorrelation between particles, that is, that you're only looking at the structure of the particle. The intensity that you measure is directly related to the density correlations within the particle, the form factor. For less dilute particles, the intensity that you measure as a function of Q is related to the shape, the form factor, and the distribution of particles in space, or the form factor times the structure factor. If you have many different sizes of shapes and sizes or polydispersity, this leads to the erosion of the features of the curve, which is to say one cannot determine the shape of the particles from a polydispersed solution because you have a distribution and the scattering curve is a superposition of all the different kinds of shapes and sizes. However, there's some very simple laws that you can apply to the low Q and the high Q behavior to still get some quite useful information. Okay, to finish off this lecture, I'm going to give you a couple of questions which will help you understand the lectures so far, if you can answer them. What I've shown here is some scattering data that's been taken off a SANS instrument, in fact the SANS instrument to the right. And if you remember, typically these measurements take two or three configurational changes. And what I'd like you to do is think about, well, what kind of configurations they've used, whether they've used enough to define the scattering curve of this particular sample series. So in the second question, I'd like you to think about experimentally how we'd separate P of Q from S of Q. And early in the lecture, I showed you a pictorial representation of a sample. So think about that sample and increase the number of particles and think about how you do that experimentally. If you like, you can use the ImageJ software to do some Fourier transforms and some radial averages to produce scattering curves. So in the next lecture, we'll be talking about making samples.